Okay, so let's start off by going through this assignment. So list the 3 types of fossil fuels used today. So that is petroleum, which is liquid, natural gas or gas, anything like that, and coal would be the main ones. And which one is globally consumed at the highest rate? I think that was petroleum on that chart that I showed you there. Describe how burning fossil fuels results in the release of solar energy. Well, fossil fuels comes from fossilized plants, and plants originally got their energy from the sun. So that's why fossil fuels are solar energy. Define the term fossil fuels. So fossilized plants and animals that over long periods of time with pressure and heat turn into a fuel source that we can use. Solar energy is just energy from the sun. A hydrocarbon is hydrogen and carbon bonded together, and we'll talk a little bit more about that today. Non-renewable means that we can't make more of it within a human lifetime. And chemical potential energy is just the energy stored in chemicals. So that's the energy in food we eat, that's the energy in fuel that we use in our vehicles. That would all be chemical potential energy. Identify the world's main energy source prior to widespread use of coal. That'd be wood and renewable resources. And as petroleum and natural gas become more difficult to extract, describe the likely effect on the price of gasoline. It's gonna make it go up. So less available, it's gonna make it more expensive, which means that we have to find some alternative fuel sources. Okay, so let's do this sample diploma problem. Sorry. There we go. Let's do the sample diploma question here. So methane gas is collected from, what's going on here? Sorry, this is the wrong question. That was like the stuff we were doing today. I was like, hey, there we go. This is the right question. So if Alberta switched to more energy efficient light bulbs, it would lessen the contribution of environmental issues. So energy efficient light bulbs, where's my marker there? So we get a lot of our fuel in Alberta. We get a lot of our energy in Alberta from burning coal, right? And coal causes SO2, which leads to acid deposition. So if we used energy efficient bulbs, we'd use less energy, we burn less coal. So it would help with acid deposition. It wouldn't help with ozone depletion because that's those CFCs, that's those aerosols. So don't select that. Coal also has particulate emissions, meaning just puts particles in the air. So it would help with that. And then global climate change, coal also creates CO2, which would lead to global climate change. So it looks like it would help with everything but the ozone depletion. So 1, 3, and 4 would be the correct answer. Okay, so let's do Hess's Law, and this is kind of a calculation-heavy lesson. So get your calculators out, and we will go through this. So explain using Hess's Law, which is this formula, leads to the prediction of heats of combustion. Okay, so when you burn a piece of firewood, where does all that heat come from, right? You look at a piece of wood, it's like, that doesn't have very much energy. But what's in there is that chemical potential energy. And that chemical potential energy is found in the bonds that hold that piece of firewood together, the actual atoms, the bonds. That's where you find that chemical potential energy. Okay. This isn't anywhere in your data booklet, and you don't need to know this, but we're going to just use this to sort of see why energy is released when you burn wood. So in wood, there's carbon-carbon bonds, and to burn anything, you need oxygen. So we also need this here, right? And whenever you burn something with carbon and oxygen, you're always going to make H2O. So H2O would have bonds like this. And then you're also going to make carbon dioxide as well. So carbon dioxide would have this much bond energy. And this is just the energy, these lines here, that's the energy that holds those two together. So if I want to break those bonds, I have to input that amount of energy, and if I have to make bonds, that's how much energy I get off. Right? And that's what this says here. So there can be endothermic and exothermic. So endothermic means it takes in energy. So if you have a molecule and the bonds are together, it requires energy to break those bonds, right? So bond breaking requires energy, and it makes them into free atoms. If you want to make new bonds, well, that's going to give off energy. So these guys are a lot more energetic, so if you link them together, it's going to lower their energy, and it's going to give off that extra energy. So bond breaking takes in energy, bond making gives off energy. So this is the combustion of octane. So this is octane 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons and the hydrogens on there. So from that chart, we saw that these carbon bonds between here would have 347 kilojoules of energy holding them together. And this has 494 from that chart. Kilojoules of energy holding them together. So to start this reaction, I need to input some energy. So I need to input this much energy to break those apart. So if I just go 347 plus 494, I get 841. So it requires 841 kilojoules of energy to start this reaction. This is why gas doesn't just spontaneously explode. You need to put in energy, and when you spark gasoline, it breaks these bonds, and that's how much we would need. So what we turn it into is we turn it into CO2 and H2O. And when we make these new bonds, they give off a different amount of energy. So from the chart, it told us that this was 707 kilojoules of energy. And then this H2O is 463 kilojoules of energy. So if I add those together, 707 plus 463, I end up getting 1170. So because these are new bonds that are being made, right, these give off energy. So if it gives off energy, we call that negative. And because this requires energy, it takes in energy, we say it's positive. So if I take my 841 and then I add it to negative 1170, I end up getting negative 392. So that means that this reaction will give off a net of negative 392 kilojoules of energy, because some energy is required to break bonds, some energy is given off when it makes bonds, and all chemical reactions are like this. They require energy, they give off energy, and what we're trying to find is how much net energy do they give off, or do they take in? Some are endothermic. Okay, so that's sort of how energy works. So this is a way of representing potential energy. So the reactants have a certain amount of potential energy, right? This delta H refers to the heat that's given off, right? So we found out that it gave off 392 joules of heat. So they have a certain amount of energy. They give off 392 kilojoules of energy, and if you give off that much energy, your products are going to have less energy. So these guys have more energy than these guys. And that makes sense. If you think of burning a piece of paper, right? A piece of paper has a certain amount of potential energy. You light it on fire, it gives off heat, and then after, those ashes don't have very much energy left over. So our products are going to have less energy than our reactants. So when energy is released during a combustion reaction, we use this symbol. Delta means change, this means combustion, and this means heat. And this means at standard ambient temperature and pressure, which doesn't really matter. So you'll see this symbol here. This just means the heat of combustion. So when energy is released during combustion, it's called exothermic, which means heat exits. And because we lose that energy because it exited, we always express it with a negative symbol. So you can't measure temperature directly, sorry, you can't measure thermal energy directly, but you can measure temperature. And what temperature is it's a measure of the average kinetic energy of the particles of a substance. So temperature and energy aren't the same thing, because if temperature and energy were the exact same thing, then all substances would heat up at the same rate, but we don't see this, right? So if you picture, so this is water, and this is a beach. Right? What heats up the water and the beach? Well, it's the sun. And the sun heats up the beach and the water the same way. But if you've been to a beach on a hot summer day, you'll know that this is really hot, and then this is really cool. So they're getting the same amount of heat, but they're not heating up at the same amount. And an easy way to explain this is if we could see the particles. So you can have big particles, and you can have tiny particles. So picture this as a ball, like a boulder or something like that, and this is me pushing on the boulder, right? So I can push on both boulders. Which boulder is going to move faster? Well, the little one. If I push with the same amount of force on each one, this one's going to be moving faster, and this one's going to be moving slower. So you can think of me in this analogy as a heat, right? I'm pushing on them as hard as I can, and how fast they move represents the temperature. So because the beach heats up really fast and really easily, this represents the sand on the beach. It's really easy to heat it up. But water is harder to heat up, so this represents the water. So the size of these particles here are represented by something called the specific heat capacity. So each substance has a specific heat capacity, and if you have a really big specific heat capacity, it's harder for you to heat up. And if you have a smaller specific heat capacity, it's easier for you to heat up. So since all substances do not change temperature at the same rate, we must define something called specific heat capacity, and that's how easily something heats up. So the definition of a calorie is the amount of energy required to raise 1 gram of water by 1 degree Celsius. So 1 calorie is 4.19. So if I have 1 gram of water and I want to heat it up 1 degree Celsius, if I put in 4.19 joules, it'll do that. Calorie with a capital C is the calorie that we find in food labels, which means 1,000 calories or kilocalories. So a calorie in food is this many joules, right? It's 1,000 times that, because a joule or calorie is a very small amount, so they work in kilocalories. So we eat food to give us energy. So when we eat food, it's the same as burning a piece of wood, right? Wood has chemical potential energy. Food has chemical potential energy. So we're getting chemical potential energy both ways. And most of our body's energy comes from carbohydrates. So before your body uses that energy, it needs to convert it into glucose. And what happens in your body is that glucose combines with oxygen that we breathe in, and then we give off CO2. That's why we breathe it out, and then water. So it's very similar to a combustion reaction, right? It's the same reaction, it just happens at cooler temperatures in our body. So when they want to measure how much energy is in food, how many calories are in food, they use a device called a calorimeter. And a calorimeter is used to measure energy changes. So this is what a calorimeter would look like. So what they do is, say we wanted to find out how many calories were in a hot dog. So they would dehydrate that hot dog, they would dry it out, and then they would crush it up into a powder. So this is a nice powdered hot dog, which would sprinkle well on your Kraft dinner. It kind of tastes good, maybe, I don't know. And then they ignite it, they burn it, and this chamber, this bomb in here heats up. And that heat gets transferred into the water. So what they do is they measure the temperature change of the water. And if they know how much water is in there and the temperature change, they can figure out how much heat is given off by that hot dog. That's what they do. So that's one way of determining heat from burning something. Another way of finding heat burning from something not in a lab is by using standard heats of formation. So another way of calculating energy released in a reaction is using heats of formation. So when we do these heats of formations, elements are given the arbitrary reference point of 0 energy, even though elements don't have 0 energy. It's kind of like 0 degrees Celsius is our reference point for 0. That's when water freezes, but it doesn't mean there's like 0 energy out there. So elements are the same thing. You can still burn elements, but we give it as our reference point. So elements are 0, and that's important. So all standard heats of formation are given on page 5 of our data booklet, which looks like this. So what this means is if I want to make ammonia, so if I want to make ammonia from nitrogen and hydrogen, it would give off that much energy if I made it. If I wanted to make benzene from carbon and hydrogen, well, it's going to absorb that much energy. So positive means it absorbs energy, negative means it gives it off. So formation just means made from the elements. So if I took calcium and carbon and oxygen and I combine them together, well, it would give off that much energy when I make calcium carbonate. Okay. So Hess's law is a way of calculating heat released in a combustion reaction from these standard heats of formation that's given in the data book. So Hess's law formula is this, which is also on page 5 of your data booklet, and it looks super confusing, but it's not as bad as it looks. Okay, so I'll explain what all these means. So this means heat of the reaction, and this means sum of. This here means mole, but we'll think of it as a coefficient. And this means heats of formation which is page 5 of our data book of our products. Okay, and this is the same thing, sum of the moles, the coefficients, the heats of formation, but it's just reactants. So it's not as bad as it looks, and I don't write this whole thing out when I do a question. Okay, so let's jump right into a question. And yeah, so I'll write out the reaction here. So I just gotta find a pen. So I'll just write out the reaction so we can see it here. So we have CH4 plus oxygen making CO2 and H2O. So you have these coefficients in front, which are important. You always need a balanced equation, and this is what we have. So remember that this is all that I write out when I do it. It's products minus reactants. That's it. That's the key part, and that'll get you your right sign. So my products are over here, and this is my reactants, right? Reactants first, products after. Products is what you make. So I'm going to focus on these guys first. And what I also need to do is I need to look at my data booklet. So when you have nothing in front, it just means 1. Nothing means 1. So this has a coefficient of 1 in front. So I'll go, actually I'll start over here, 1 times, and I have to look up the value for this. So the value for that heat of formation, I thought I had this open. Sorry, I'll have to open it up again. Oh, I do have it open. I don't know what it's under. It's page 5 here. So we need to look up carbon dioxide. So here's carbon dioxide, and here's the value that's given here. So negative 393.5 kilojoules is what we want to put in there. So we look that up, and I go negative 393.5 kilojoules. And I put a bracket around that. Okay. And because it's sum of, I have to add it to my other product, which is water. So there's a coefficient of 2 in front, so I'll go 2 times, and I have to look up the value for water. And water you have to be careful of because there's 2 values for water. So you always need to know the state of your water. So we can see the state of this water is gas. So I'm going to include that in here, and I need to look up the gas value of water. Where is that? Oh, it's in Internet Explorer, that's why. Sorry. So you can see that there's water gas and water liquid. Well, we want to look up the water gas value, which is negative 241.8. So that's what I'm going to add here is negative 241.8 kilojoules. Okay, so these are both my products. So after I put my products together, I'm going to put a big bracket around them. I need that because that's how I'm going to type it into my calculator. Okay, and then I'm going to subtract it from my reactants. So there's nothing in front of this. So I'm going to go 1 times, put a bracket there, and I have to look up this, which is methane. So when I look up methane, which is CH4, it's negative 74.6. Okay, so I'm going to plug that in here, negative 74.6 kilojoules. Okay, and then I'm going to add that to, so I have 2 oxygens, so 2 times. And if I look up oxygen on my chart, oxygen, oxygen, oxygen. There's no oxygen, but remember that elements are given a value of 0. So if it's just oxygen with nothing else, it means it's an element. So it's given a value of 0. So I'm going to go times 0 kilojoules, and then I'll put my brackets around my reactants. Okay, now I'm ready to type this into my calculator. So I'm just going to make this a little bit smaller so I can fit it on here. Okay, you want to type it in exactly how we wrote it out. So we'll double bracket to start, and then I'm going to go 1 times negative 393.5, and then I'm going to close my bracket. Okay, and then I'm going to add it to, open a bracket, 2 times negative 241.8. And then you can see I have a double bracket on the end like that. So I need to put a bracket around my products. And then I'm going to subtract my reactants. So I'll double bracket again, and I'll go 1 times negative 74.6. Close my bracket here. And then I'm going to add on, open a bracket, 2 times 0. And 2 times 0 is 0, so we won't put that in for the future, but I'll just put it in now, and you can see I double bracket around the end. Okay. If I plug that all in, then I get the right answer. So the energy given off in this combustion reaction is 802.5 kilojoules. And that's my answer. Okay. So let's do another one. Okay, so we're going to do this one. So this is the combustion of ethanol. And we only do combustions, so it makes it a little bit easier. So I'm just going to write this reaction out. C2H5OH plus 3 oxygens turning into 2 CO2 and 3 H2O gases. Right, so the only one we really have to worry about for the state is water. We have to make sure that we know that it's gas, but this is what my reaction looks like. So again, I want to do products minus reactants. Okay, these are my products, these are my reactants. So I have 2 carbon dioxides, so I'm going to go 2 times, and I have to look up that carbon dioxide again. So 2 times negative 393.5. Okay, so I put that in there. And then I'm going to add it to my other product, which is H2O gas again. So I'll go 3 times, and I'll look up that value for H2O gas. So that's on the bottom. Water gas is negative 241.8. Put brackets around that, and then put a big bracket around all of your products. We're going to subtract our reactants. So we have this, which is ethanol. So we'll have to look up that. Oops. So if we look up ethanol, here it is right there. It's negative 277.6. And then there's one of them because nothing is shown there. Oops. Right. So there's one of them. And then we'll times it by negative 277.6 kilojoules. So just double check that that's the value. Yeah, 277.6. And we also have 3 oxygens, but oxygen's going to be 0. So I'm just going to leave that out there because, well, there's no real point in putting that in there because it's just going to be 3 times 0. So I'm going to plug this into my calculator. So double bracket to start. 2 times negative 393.5. Close my bracket. I'm going to add on 3 times negative 241.8, double bracket at the end, and then I'm going to subtract 1 times negative 277.6, close my bracket. I only need one bracket around these ones because there's not two things in there. So I get the answer of negative 1234.0 kilojoules. Okay. Cool. So let's try a board question now. I'll get you guys to do it. So pause the video, see if you can do this on your own, and then I will do it right now. So make sure you pause the video. And I'm just going to write out the reactions. Just give me a sec. 2C4H10 plus 13 oxygen, 8 CO2, and 10 H2O gas. Okay, so I'm going to do these first. So I'm going to do my products minus reactants. So I'm going to go 8 times CO2, which is negative 393.5 kilojoules. And then I have 10 H2O gas, so negative 241.8 kilojoules for the H2O gas. Put big brackets around my products, and then I'm going to subtract 2 times my butane. So I'll have to look up that butane, which is negative 125.7. And I'm just going to leave my oxygen out of there because 13 times 0 is 0, so it doesn't affect my equation at all. And I'm ready to plug in. So 8 times negative 393.5. Close my bracket. I'll add it to 10 times negative 241.8. Make sure you put in those negatives and your double brackets. And then we'll subtract 2 times negative 125.7. Oops. 5.7, and then close my bracket, and you end up getting negative 5314.6 kilojoules. And if you didn't get that, just send me an email and we can go through any questions that you want to go through. Okay, so efficiency. So all energy calculated using Hess's law does not always make it to you. So lots of energy conversions have to happen before that energy can make it to the consumer in a usable form. So we talked about the energy conversion in a coal power plant, right? We start with that chemical potential energy. We heat it up, and it heats up the steam. Steam turns into kinetic energy, turns that turbine, turns the generator, and turns into electrical energy like that. So say every step you lose 10%, 10%, 10%, 10%, right? There's all these energy conversions, so you always lose a little bit of energy. So say if we calculated it to be, well, the last answer, 5314.6 kilojoules of energy. Well, if I take off 10% of that, then 10% of that, and then 10% of that, we might only get like 3,000 kilojoules of energy in the end because we lose it. So to make something more efficient, you want to have less steps, less energy conversion. So we'll talk about more efficient devices and how they have less energy conversions. Like an electric car has way less energy conversions than a gasoline car, and that's why it can be a lot more efficient than a gasoline car. Okay, so that's it. We'll do that sample diploma question tomorrow. I'll remember to post an assignment today, and that's all. So if you have any questions, shoot me an email.